All right, in this lesson, we're going to do a review of atomic structure and we're going to dig in a little bit to electron configuration. So first thing we're going to review are the three subatomic particles that you need to know. The first is the proton. So in our model of the atom here, our proton and neutron are located in the nucleus, or the center of the atom. Okay, protons have a mass of 1. Neutrons have a mass of 1. Okay, now electrons have mass. I know it says 0 here. Electrons have mass, but their mass is so much smaller than the mass of protons and neutrons that for the purposes of our class, we're going to consider they have a mass of 0. Okay, now our protons and electrons have a charge. Protons have a positive charge, electrons have a negative charge. Neutrons, neutron looks like the word neutral, neutrons do not have a charge. Okay, so that should hopefully be a recap from Chem 1 or honors chemistry. Okay, couple things we need to just review here. So the number of protons correspond to the atomic number. So if I go to my periodic table and I look something up, like hydrogen is number 1, it has 1 proton. Helium is number 2, it has 2 protons. That atomic number represents the number of protons. An atom is considered neutral if the number of protons equal the number of electrons. Okay, an ion is when you have the protons don't equal the electrons. So you're going to have more protons, positive charge. More electrons will be a negative charge. All right, the number of protons plus the number of neutrons equals the mass number. Okay, so got a little screwy here. So our mass number is X. So when you see something written in isotopic notation, you'll see the mass number up here. That is where you would find your mass number. That's the number of protons plus the number of neutrons. When it's written like this, where it's the element dash a number, that number right there is the mass number. All right, electron configuration is the arrangement of electrons in an atom. Okay, we're going to go through a couple of examples here where we're going to work through electron configuration. There are 3 principles that we always want to follow when we're doing our electron configuration. The first is the off-bow principle. We always want to start with the lowest energy level, which is going to be our 1s energy level. So let me just give you an example here. So if I were filling this in with electrons, I would always want to start with my 1s orbital before moving on and filling anything else. Okay, so if I started in the 2s orbital, that would violate the off-bow principle. All right, the Pauli exclusion principle. Only 2 electrons can go in an orbital and they must have opposite spins. So those are 2 electrons going the same way. Those are 2 electrons going in the opposite way. So this is no good. This is what we want to see. Okay. Hund's rule states electrons enter orbitals in the same energy, 1 level at a time, and then pair up. Oops. So let me show you what I mean here. So if we're drawing electrons, so I'm going to actually fill these in correctly so far. When I get to the 2p orbital, I want to make sure everybody gets 1 before I go back and double up here. Okay, I like to call this the buffet rule. Everybody gets 1 before they go. Everybody gets first before you go back for seconds. So this would be a violation of Hund's rule, where I have 2 electrons in the same orbital. All right, let's do an example. Create an orbital filling diagram for oxygen. Okay, so oxygen has 8 electrons. So I need 8 places for electrons to go. So we've got our lowest energy level, which is 1s, then 2s, and then we have 2p. So let's go ahead and let's fill this in. So 8 electrons. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, now if you have a hard time remembering the order that these orbitals go in, I have a trick for you. So 1s, 2s, 2p. So every time I go down a row, I'm going to increase the number by 1. 3s, 3p. And then every time I add a row, I'm also going to add a letter. So after 3p would be 3d. I'm going to add a number, 4s, 4p, 4d. And then after D comes F, 4F. I'm going to do one more row here. 5S, 5P, 5D, and then 5F. Okay, now I'm going to draw some diagonal arrows here. So if you notice, starting here, I would hit the 1S, and then I'm going to basically go back up to here, and then I go to 2S, and then I'm going to go back up to the next one, and then I hit 2P, 3S, go back up here, 3S, and then it is 3P, 4S, okay, just follow this, 4S, 3D, 4P, 5S. So that's an easy way to remember it if you have a hard time following along on the periodic table. Okay. All right. Write the shorthand and noble gas notation for oxygen. Okay. So I know that it has 8 electrons. So we're going to need to fill 1s completely. That's 2. 2s we're going to fill completely. And then I've got my 2p. So this is what we just did. 2, 3, 2, 4, 6, 8. Okay, so this is what we just did with our orbital filling diagram. And to take that and turn it into notation, so if you look here, I have 2 electrons in the s. So I'm going to put a 2 right here. I'm getting that from right here. 2s. And then I had 2 electrons there. Again, I'm looking at how many electrons are here. And then in the p, 2p, we have 4. Okay. You don't need to draw the orbital filling diagram every time, but I just want to see, I want you to get a good visual of where these are coming from. Okay. Now, to do the noble gas notation, we're going to need to pull up a periodic table. So let's do that. Okay, so here's our periodic table, and oxygen is right here. Oxygen is number 8. We want to count backwards until we get to a noble gas. Remember, noble gases are this last column or group on the periodic table here. So let's count backwards. So 7, not a noble gas. 6, not a noble gas. 5, not a noble gas. 4, not a noble gas. 3, not a noble gas. Now we go all the way back to the other side of the periodic table. 2 is a noble gas. Okay, so helium is a noble gas. So I start with that noble gas, helium. So I'm going to put that in brackets. Okay, helium is number 2 on the periodic table. So what we're going to do is we're going to basically replace the first 2 electrons with helium. So we're going to basically pick up from where we left off after those first 2 electrons. I'm going to take this next piece and I'm going to insert it. So 2s2, 2p4. So when you write a noble gas notation, you're basically replacing all of the electrons up to that noble gas with the noble gas in brackets, and then you just kind of pick up where you left off. Okay, so again, helium is number 2, so I'm accounting for 2 of those electrons, and the last 6 I write out in regular electron configuration. I write out the regular, or the rest of the electron configuration, rather. All right, there are some exceptions, copper and chromium. So I just want to show you here. So copper, for example, if we were writing this out in noble gas notation, I would fill up the S, and then I would have 9 left to go into the D. But what happens is we actually take one of those S's and put it into the that last D to completely fill that up. Chromium, same thing. Okay, so we've got 2 and 4. That's what we would expect. So we actually take 1 and we move it over to that D to fill that up. Those are 2 exceptions, copper and chromium. All right, Coulomb's law. We use that to calculate the force between 2 charged particles. Okay, so I've got Coulomb's law. I've got the whole formula written out here. So Q1 and Q2 are in the numerator. Q1 represents the electrical charge on particle 1. Q2 represents the electrical charge on particle 2. Okay, R, I like to think of that as the radius or the distance between them. That's the distance between our 2 particles. Okay, so in our example here, I have particle 1, particle 2. They're being attracted to each other. I've got a positive particle and a negative particle. Remember, opposites attract. So the force of attraction is what we're calculating here. Okay, that F does stand for force. If they were the same charge, so if I had a positive and a positive, or a negative and a negative, I'd be calculating the force of repulsion. One thing I want to point out about Coulomb's law, and this is kind of important here, the radius is squared. So that means the closer you are, if they're being attracted, or the closer they are if they're being repelled, that force is going to get a lot stronger the closer you are. The further away you are, the more of a drop-off you're going to see in that force, because the radius is being squared in our formula here. All right. Ionization energy. Coulomb's law can be used to predict the amount of energy required to move an electron from an atom. Electrons further from the nucleus take less energy to remove. Electrons closer to the nucleus take more energy to remove. Okay, so why is that? Well, here is our nucleus. Okay, I'm just going to shade that in. It's going to be a pretty basic diagram here. So we've got 2 electrons on the inside here, and let's go ahead and let's fill in 8 on the outer ring. So remember, electrons have a negative charge. Okay. The nucleus has a positive charge. So again, opposites attract. So these electrons that are really close to the nucleus have a very strong attraction compared to these electrons that are further away from the nucleus. Okay, that distance is greater between those outer electrons and the inner electrons. So again, looking back at our formula, that radius really impacts the amount of force. So the further away you are, the less of a force of attraction you're going to feel, the easier it is to knock those away. The inner electrons are a lot closer. There's a stronger force, and it takes more energy to knock them away. All right, so let's take a look at this table. So up at the top here, these are the electrons. That's essentially what these are representing. Okay, so sodium, for example. Sodium is number 11 on the periodic table. Its outer shell is the S block, and it has 1 valence electron. Okay, so if you look 496, that's the amount of energy that it requires to knock that valence electron out. There's a huge jump here to the next electron to knock that out, because that's an inner shell electron. It takes a lot more energy to knock that out. Magnesium has 2 electrons in its valence outer, or 2 valence electrons in its outer shell here. All right, and then this third electron is an inner shell electron. So again, going back to our diagram here, I'm talking about the inner electrons here, not the outer ones. Okay, so those inner ones, remember, are a lot harder to pull out. So it requires a lot more energy. And you see there's a huge jump in the amount of energy here. Okay, so that's essentially how we read this chart here. Okay, so the big takeaway from this lesson is it takes more energy to knock out an electron that's closer to the nucleus than it does to knock out an electron that's further away from the nucleus.